Welcome everyone to this first video here talking about specific changes in entropy. Okay. So in the previous video mentioned that the entropy change for say a phase change is just the enthalpy change of that phase change divided by temperature. Here we're going to look at an isothermal expansion of a gas. Okay. So we know ds equals dq reversible divided by T, okay? For an isothermal expansion of a gas, whether it's done reversible or irreversibly, we can imagine a path that connects the same endpoints and start points as a reversible path, right? So let's say I start here and there, right? If I do this irreversibly, right, I can do the exact same type of change, but reversibly, okay? That's assuming constant temperature, okay? And you can do this basically as long as temperature, pressure, or volume are held constant, this works, okay? Where a single path will connect those same initial and final states. And so, so for an isothermal expansion, if it's done reversibly or irreversibly, I can imagine that it's done reversibly, right? And calculate the entropy change along that path. Because the entropy change for the irreversible path will equal the entropy change for the reversible path because entropy is the state function. It's just I do not know how to calculate the entropy for an irreversible path because entropy is defined as the reversible entropy or reversible heat. Okay? So we know for a reversible isothermal process that heat transfer is just nRT dV over V. Okay, that's obtained from the fact that dW equals minus dQ, right? And so ds, plugging in for what dQ reversible is just nR dV divided by V. So we just integrate that out, right? And you get that change in entropy for an isothermal process of an ideal gas is nR ln V2 over V1, or V final over V initial, okay? And again, this isothermal expansion can be done reversibly or irreversibly, and I would get the same entropy change because entropy is a state function. But to derive this expression, we had to find a reversible pathway to calculate what the entropy is. Okay. Next, talk about the entropy change for the heating of a gas at constant pressure. So again, dq reversible, right? For a constant pressure process is just going to be related with Cp dt, okay? Because reversible, right? So, reversible means things are at equilibrium, which means mechanical equilibrium, which means P equals P external, which means, dH equals dQ, right? And dH is Cp dt, okay? So dQ for reversible constant pressure heating, right, is equal to Cp dt. Right, and so entropy changes the integral of Cp dt divided by T. If Cp is constant, then I can pull that outside the integral, and I'm just left with the entropy change for a constant pressure heating or cooling of a gas is just Cp ln T final over T initial. Okay, and what do we think this is for constant volume? Right, it's going to be the same expression but with Cv, right? For a constant volume process, now dq is equal to du, right? And du is Cv dt, so you get the same final expression just now with Cv, right? So delta S Cv ln T final over T initial, right? For a constant volume process, constant pressure process with Cp, okay? Right. And then we'll talk about reversible adiabatic expansion of a gas to finish this up, right? For that, I have a reversible process already, and it's an adiabatic process, which means dq is equal to 0. So ds is equal to 0, right? And so the entropy change for reversible adiabatic expansion is 0 for your system, okay? Right. However, delta S is not 0 for an adiabatic expansion that is not reversible, okay? And in the next video, we'll talk about what this is, okay? But for for now, right, in this video, just note that this is not true that delta S equals 0 for an irreversible adiabatic expansion. It only equals 0 for a reversible adiabatic expansion.